In this video, we're going to look at operations on matrices. The first thing we need to discuss, though, is what is a matrix? A matrix is a rectangular arrangement of values that are put into rows and columns. So an example of a matrix might be like this. It's enclosed in large brackets, and the rows are horizontal, and the columns are vertical. Now, something about me is I went to Rhodes College in Memphis, Tennessee for my undergrad degree in mathematics. And there I had a professor who told us that we were really lucky we went to Rhodes College because when we describe a matrix, we describe it based on its rows times or by its columns. So we will never forget the order that we list our rows and our columns. So if I were to say that this is matrix A is equal to 3, 2, 1, 2, 4, 6, I would describe its size as 2 because there are 2 rows by 3 since there are 3 columns. Now if I were to talk about multiple of these things or plural of these things, we would say matrices instead of just a singular matrix. So let's get into it. If I want to determine the order of the matrix is described just like I just explained, the rows by the columns. So a matrix with m rows and n columns is an m by n matrix. Okay, rows always comes first and then the columns. So if I were to determine the order of the matrix in example 1, we would say this is a 2 by 2. In 2, we have 1 row and 1, 2, 3, 4 columns, so 1 by 4. In example 3, we have 3 rows and 1 column. In example 4, we have 2 rows and 1, 2, 3, 4, 5 columns. So you can see finding the order of a matrix is not too terribly difficult. You're just counting the rows and counting how many columns there are. Now, there is a general way to represent a matrix based on its elements. The elements, if we look at this example, we have A, I, J. This is saying the matrix created by the elements in these positions, okay, is equivalent to the element in this position 1, 1, the element in position 1, 2, all the way till we get to AM, 1M. Okay, and then we do the same thing 2, 1, 2, 2, all the way to 2M. Because remember, we're doing M by N matrices. This is how many columns there are. So if I'm counting from 1 all the way up to M, and then in the rows, we're counting all the way down to N. The notation Aij represents the element in the ith row and the jth column. For example, A23 represents the element in the second row in the third column. Now remember, if I'm thinking about this, if I have Aij, I can think of this as a row column. Okay, it's telling us which row and which column it is in. Again, it goes in that order, row before the column. So, given the matrix A in this next example, we're going to determine the value of the given element in the matrix. So, A sub 1, 2, it's in the first row, second column. So I look here, first row, second column, that's the square root of 3. For the second one, I'm looking at A sub 2, 2. So second row, second column. So second row, second column, that value is pi. And then the last one, A14, I'm looking at the first row, the fourth column, that value is a 0. So we use this notation to find elements in certain positions within a matrix. Looking at adding and subtracting matrices, we have to make sure that they have the same exact order. The sum and the difference are found by adding or subtracting the corresponding elements. So if I have a matrix or two matrices that have the same order, I can add or subtract them. And we do this by just adding each corresponding element to each other or subtracting them if it's a subtraction problem. So in the first one, we're taking the matrix 1, negative 8, 5, 20. We're subtracting the matrix 2.3, 5, 0, negative 12. Okay, so if I think about this, all we're doing, it's the same order because this one's 2 by 2 and this one's 2 by 2, so the same order is satisfied. So for each new element of our resulting matrix, we would take the elements in the row 1, column 1 position and subtract. And then in the row 1, column 2 position and subtract, so negative 8 minus 5. And then the row 2, column 1, so 5 minus 0. And then row 2, column 2, so 20 minus negative 12. So our resulting matrix, we're just going to do that subtraction, is going to be negative 1.3, negative 13, 5, and 32. Looking at example number 9, we have the order of this first matrix is 1 row by 3 columns. The order of the second matrix is 3 rows, 1 column. This I cannot subtract. I cannot subtract those because they do not have the same order. The order of the matrix must be exactly the same. And the order, I'm using air quotes, but the order of the rows and the columns matters. So the rows have to come first, and then the columns. 1 by 3 is not the same thing as 3 by 1. And so therefore, I cannot add these together. If you think about what these elements are, this one is A1, 1, A1, 2, A1, 3. The elements here would be A1, 1, A2, 1, and then lastly A3, 1. These are not the same, and so therefore I cannot subtract. Those are the nice ones. So when you can't do anything to it, you just say, I can't do anything to it. Saves us a little bit of time. There are two types of multiplication with matrices. The first one is scalar multiplication. The product of any real number k and a matrix, we'll call it matrix M, is called scalar multiplication. The real number k is called a scalar to distinguish it from a matrix. To multiply a matrix A by a scalar k, multiply each element in the matrix by k. So essentially, you can think of that scalar value multiplying times every element inside the matrix. And so for this first one, for number 11, we would end up with the resulting matrix, negative 6, 1, and 1.6. Because I just multiplied each element inside the matrix times 2. Looking at the next example, this is kind of an order of operations problem because we have multiplication and we have subtraction. So we have to go way, way, way back and think about whether or not multiplication comes first or the addition and subtraction comes first. We follow the order of operations. Multiplication and division comes before addition and subtraction, and so therefore I must multiply by the scalar first. So I'm going to do 5 times that first matrix, which will result in negative 10, 20, 30, and 5. Then I'm subtracting that second matrix. And so my result, I can show my work. If you would like to see that, I would have negative 10 minus 10. That's from that first element subtracted from that first element, having the first element of the second matrix subtracted from it. Then I would have 20 minus negative 25. Then I would have 30 minus 30. And then I would have 5 minus 4. There we go. So my end result is going to be negative 20, 45, 0, 1. And that is my answer to this problem right here. Here we have a linear combination. So in this linear combination, what we're doing is we're substituting in the values and figuring out what our matrix X has to be in order to make this linear combination true. So I'm going to substitute in my matrices into this equation that's been provided. So I have B, which is negative 2, 10, 1, and 8, minus 2 times x. So what I'm going to do is I'm going to call this x11, x12, x21, x22 has to equal my A matrix, which is 4, 6, 5, negative 3. So essentially we have here a very small series of 4 equations where we're solving for x. Now remember, we're going to multiply by that scalar first. So we end up getting our first matrix stays the same. But each of these gets multiplied by 2 in the second matrix. So we essentially have 4 kind of sub-problems here, because I need to have negative 2 minus 2x11 equals 4. So I have to solve this one to figure out what x sub 11 is. Solving this, I'm going to add 2 to both sides, so I get that negative 2x equals 6, divide by negative 2 on both sides, and so I get x sub 11 is equal to negative 3. I'm going to write that up here. Okay, we're going to do that with each of these. So the next one is 10 minus 2x12 equals 6. Subtract 10 from both sides, so I get negative 2x12 equals negative 4. Divide by negative 2 on both sides. My work's getting slightly cut off, but I'm dividing by negative 2 on both sides. And I get that x sub 12 is equal to positive 2. Doing the same thing, 1 minus 2x sub 21 has to equal 5. So 1 minus 2x sub 21 equals 5. Subtract 1 from both sides. I get that negative 2x21 is equal to 4. Divide by negative 2. So x sub 21 is equal to negative 2. And then lastly, 8 minus 2x sub 22 is equal to negative 3. Subtract 8 from both sides. I get negative 2x sub 21 equals negative 11. Divide both sides by negative 2. And I get x sub 22 is equal to 11 halves. Now you could um, you could write that as a decimal value. Okay, unless it explicitly tells you to write it as a fraction, you can put that in your calculator, do 11 divided by 2, and you would get 5.5. So you can write it as 5.5. I'm going to leave it as a fraction. They're equivalent, and so I don't want to chance making a mistake from that point on. So my matrix X is equal to -3, 2, -2, 11 halves. And that's my answer. This sums up our basics on operations with matrices. In the next video, which actually goes along with lesson 8, we're going to take a look at determinants of matrices, and we're going to look at the Cramer's rule. Cramer's rule is a way that we can solve systems of equations, which I love. So I'm looking forward to going over that video with y'all. If you have any questions, email me and let me know. Thank you.